Hello, this will be a demonstration of proposition 11 from book 10 of Euclid's Elements, which says that if four magnitudes are proportional, then if the first is commensurable with the second, then the third will also be commensurable with the fourth. But if the first is incommensurable with the second, then the third will also be incommensurable with the fourth. So we'll have four magnitudes, A, B, C, and D. They will be proportional. So A is to B just as C is to D. And will either be the case that A is commensurable with B or A is incommensurable with B. Now, if A is commensurable with B, then we will want to prove that C is also commensurable with D. But if A is incommensurable with B, then we will want to prove that C is incommensurable with D. Now first, if A is commensurable with B, then we can say, according to proposition 10.5, that the ratio which A has to B will be the same as a ratio of two numbers. That's what proposition 10.5 tells us. But we can also know from our given that A is to B just as C is to D. So now we have two ratios, C to D and number to number, and both of those ratios are the same as one ratio, A to B. So we can say, according to proposition 5.11, that those two ratios are also the same as each other. So that we can say that C is to D also as a number is to a number. But we know, according to proposition 10.6, that this means C is commensurable with D. That proposition, 10.6, what it tells us is that if the ratio of two magnitudes is the same as a ratio of two numbers, then those two magnitudes will be commensurable. So that because C has to D a ratio which a number has to a number, then C will be commensurable with D. But if, on the other hand, A is incommensurable with B, then the ratio which A has to B will not be the same as a ratio of two numbers. We know this from proposition 10.7, that incommensurable magnitudes, the ratio of incommensurable magnitudes, is not the same as a ratio of two numbers. But we also know from our given that A is to B just as C is to D, so we can conclude from this, because A is to B just as C is to D, and A is not to B as any number is to any other number, then we can likewise say that C is not to D as any number is to any other number, that the ratio which C has to D is not the same as a ratio of two numbers. But this means, according to proposition 10.8, that C and D are incommensurable. Proposition 10.8, that tells us that if the ratio of two magnitudes is not the same as a ratio of two numbers, then those two magnitudes will be incommensurable. So that because C is not to D as any number is to any other number, we can conclude that C is incommensurable with D. And this is what was required to be proved. We wanted to prove that if A is to B just as C is to D, if we have four proportional magnitudes, and if the first A is commensurable with the second B, then the third C is commensurable with the fourth D. But if the first A is incommensurable with the second B, then the third C will be incommensurable with the fourth D, and we have just demonstrated that. So that being what was required to be proved, we are therefore done with the proposition, therefore, etc., Q, E, D. We're starting to see with this proposition that commensurability and incommensurability is a similar sort of relationship as greater than, equal to, or less than. Well, remember, we've seen this many times, that if we have four magnitudes which are proportional, then if A is greater than B, C will also be greater than D. If A is equal to B, then C will be equal to D. And if A is less than B, then C will also be less than D. And we've just demonstrated that the same holds for commensurability and incommensurability. So just as equality and inequality transfer over proportion, as it were, we're seeing now that commensurability and incommensurability likewise also transfer across proportion. That's all I've got to say about this proposition, so I will end the video here and move on to proposition 10.12.